Now I want to devote a few next lectures to point problem. This is the following problem. We return to the Lagrangian description of the fluid. The domain M, the plane, and you have velocity v at t, and we follow the trajectories of the particles. So if the particles were initially at the point x, then at the time t, they're at the point f e of x. Yes, this is the flow. So ft is such that ft of m equals m. No, in particular, the boundary is transformed into the boundary, and the Jacobian identically one. And the group of this, the set of this F forms a group. No, for now, it's enough. Now, the U of xt equals L dot yeah, so it is the velocity of the particle, which at the moment t is at the point x. So we have to find this particle. We have to locate where it was initially, yes, and find the time derivative of location. And the energy is just square of L norm, no, with factor 1/2. The action is integral from 0, no, say from 0 to 1. All our motions are from t 0 to 1, for example. Dt equals integral from 0 to 1, integral over n out dot. Everything is smooth for now. So I don't go to some singular things. And now 2-point problem. Find trajectory of the fluid Ft in such that F0. No, we can always assume that initial condition responds to identities. We have to find some mark some point in Z. Let's mark this identity mass. Yeah. F1 equals F, it is given. And what is in between? What is in between? Let me, J, this is action from 0 to 1. It is no, so it is action. Action is integral of kinetic energy. No, if there is no potential energy, then we have to take the difference between kinetic and potential energy. So it is a Lagrangian, the energy is Lagrangian, and this is Lagrangian action. Yes, and principle. That the fluid trajectory is such that it is a stationary point for the action. The famous least action, it has many names and many formulations. It can be called McCarthy, may be called Hamilton, maybe some other names, but general thing is that this action should be stationary. Then, as the Euler equation for this problem stationary among of t satisfying the boundary boundary condition this. Boundary condition. No, in particular, why I write least action, no, it is traditional name, of course, and there is some sense that we can to find the solution, the trajectory which reduces the stationary point of the action functional, we can find the question.
Yeah, could you maybe define the variation or write down how it is defined? Because I cannot really.
Variation.
Yeah, I guess the variation must be some perturbation in the class of D.
Yes, so here is the functional. Yeah. So let us find the variation. So the variation Ft plus delta Ft. Yes, delta Ft is variation. So the point particle from point S move to point Ft of X, and then it moved to some infinitesimal delta Ft, also some infinitesimal.
And how does this infinitesimal shift look like? How can we ensure that it stays in the class?
Let me first, all right, infinitesimal vector field, delta Ft should be incompressible. It should preserve this condition. Yes, this means that its divergence is 0. Yes, and to preserve this condition, it should be tangent to the boundary on the boundary. Yeah. So this is delta ft. So here of ft plus delta ft equals integral from 0 to 1, integral over m, 1/2 modulus ft plus delta ft squared, the x of x, the f dt equals integral from 0 to 1, integral over m, 1/2 ft of x squared plus ft of x square product with delta ft of x plus no, okay, all small of delta ft. Yes, the square of this vector, length of vector, it is product, product vector with itself. Yeah, so it has this form. Gives that's the equals ft from 0 to 1, this part. This term is the same as for the action. Yeah, you have to find the variation. It's this term. Plus integral 0, 1, integral over m, ft of x, delta ft of x, the m dt plus delta ft. Like this. Yeah. So delta j ft equals integral 0 to 1, integral over m ft delta ft dx dt. Yeah. Now delta ft equals yes. Now to be stationary means that variation is 0. Yeah. Or any delta ft such that divergence delta ft is 0, delta ft on the boundary equals parallel to the bound, like this. Yeah. So this means that I'm sorry, ft dot. So yes, everywhere this. Now, we have a vector field. No, I would say vector function ft dot, which is orthogonal to all the functions of the sort that they have divergence 0 and they are tangent to the boundary. Yeah. So let us define say x equals the set of the set V in L2 M R2 such that divergence V is 0 and V and on the end equals 0. Y, the set of W in L2, Y W is gradient some P. Yeah, potential vector field. And we know that L2 M R2 equals orthogonal sum. No, Holt decomposition or sometimes referred to Helmholtz. No, many names of this. Yeah, and so this means that F T dot T minus 1, yes, it is like vector field, is orthogonal to X. Yeah, because this variation is 0. It is what is written here. And delta Ft dot is from the space X. Yeah. Hence, Ft dot T minus Y belongs to Y. Yeah. If it belongs to Y, this means that belongs to I for any T. Because here is also the time integral. Yes, but we can vary this variation arbitrarily depending on T. So it is true for any fixed T. So this means that there exists a function T x T, let me call it Y T, such that ft dot of x equals minus gradient p of ft of x. Yeah. So we have to here we always have to say label the vectors either by the point x, then it is velocity of a particle, or by the y argument y, which was ft of x. So there's the point where this particle finds itself at this moment t. So this means that acceleration of the particle is equal to minus gradient some function p, scalar function, potential function. Yeah. Now we can call this p pressure. Therefore, it is denoted by p. That's it. This is the meaning of this variational problem. Yes, and now how to find? One thing is to define to write down the equation. Other is to solve it, and how to find this solution, this velocity, this fluid motion. So here I try to be consistent and consider fluid motion in Lagrangian framework. How to do it? So we consider more constructive problem. Find ft such that action ft from 0 to 1 minimum is the same boundary conditions. So let me tell you in advance what is today's status of this problem. We have two problems: to find stationary point, yes, or critical point of this functional action, and to find the minimum of action. So the general problem, find the stationary point, is for now wide open. So there is a hypothesis that this problem is always solvable, has solution for any given diffeomorphism F, the final position of all the particles. So this means the fantastic things. We prescribe final position of any fluid particle, and then we can push initially our fluid in direction of some vector field, such that at time 1, each particle assumes its prescribed position. Yeah, this is very far from solution. I would say almost no ideas. Problem two, that was problem one. Problem two, find with minimal in some weak sense. This has solution, and I'm going to explain in which sense. But this solution can be, say, discontinuous, or even maybe even more singular. But the peak of this is that the velocity field is well defined and is a weak solution of Euler equation in the sense which I will also describe. Yeah, so it produces as a weak solution. As for existence of smooth solutions, almost sure it is wrong of this problem. So the smooth solution in some explicit cases, which we know, no, I would say that numerical study of this problem shows that the smooth solution may not exist. The deep reason for this is that the variational problem to minimize the action is degenerate. It includes the function includes the space derivative of unknown of this they include the time derivative, yes, but does not include space derivatives. Yes, so it is very much degenerate, and it is hence there is no reason for it to have a good minimizer. But again, one thing is to say that we don't see the proof of existence of smooth solution, and others say to produce example when the solution really does not exist. Maybe because people did not work hard enough to do it. Me included. Yeah. So now I wanted to stop a little bit on this problem. There is another problem, a physical problem, and we start from physics. It is Sakharov. George. Problem. No, Arnold is started later, but no, mostly it's called Sakharov. Sometimes it's Deutsch Sakharov. So what is this problem? It appears in, say, astrophysics and on some other domain. Suppose we have domain, say, M, in three-dimensional space. And we are given a vector field, say, V of X. Vector field in M such that divergence V is zero. But we can apply different boundary conditions and not apply condition at all. This gives us different versions of this. Now, consider again, consider the group of volume preserved diffeomorphisms of this domain M. And if F in G, consider the group vector field push forward of B. We'll say BF. So we deform this, say, fluid, and vector field also changes. So start of B of Y equals F prime of F minus 1 of Y times B prime of B of Y, Y it is there, equals, first you take B minus 1 of Y times F prime of F minus Y of Y. So this is no 3 by 3 matrix, derivative of the mesh. So we take at the point x move to y, and we move back here, but before we or after we multiplied by derivative of transformation here. Yeah, no, for example, if f of y, f of x is the same as x, it is a fixed point, then the vector multiplied simply by this derivative. Yeah. This is how magnetic field is transformed in well-conducting medium is transformed when we deform this medium. And then we write the functional energy integral over M energy energy of F of D integral over M module B of F square dx. Yeah, that's magnetic energy. And then for any f, we can consider functional, which is energy of Bf. Bf is this, what is written here. Yeah. And this system, because it is a fluid, it can move. is tending to carry this magnetic field in the direction of decrease of its magnetic energy. Yes? So try to minimize it. The question is, does the minimum exist, and what is the nature of the minimum? What happens with the fluid? No, for example, the domain M is interior of a star. Yes, it is plasma, it is well conducting. There are powerful magnetic fields which set in motion this interior of the star. So what is the final configuration? Or it is the solar corona. In the solar corona, we have different, things like prominences, the arcs of magnetic lines, yes, and it also wants to assume configuration of least energy. What will happen? No, physicists and astronomers, yes, and also it may be plasma in tokamak, for example, yes, or it can be, say, the molten metallic core of Earth, where also we have powerful magnetic field. And so we have a more or less universal problem. And this problem is also wide open. And for now, we consider only some particular cases of this, or limit cases. Not one case. M is two-dimensional. Yes, it is especially, I would say, attractive because it's easier, and we can here cheaply make numerical experiments. In this case, we have no, there is rigorous results that solution exists, and in some class, and numerical result that yes, it exists, but usually it is discontinuous. Maybe next time I will bring some pictures which confirm this. And second result is the following. It can be called partial fields. Partial means close to the axis. So our domain in this case is a long thin cylinder, which is a base M, it is base in the plane. Now, the magnetic lines, lines of magnetic field B, are going, no, its direction is close to the axial direction. Yeah. Now, in this case, if you follow magnetic line, if you start at the point X on the base, then we have some trajectory, this projection of magnetic line on the base, M. Yes? So we have some trajectory, X equals Z, and here F of X, Z. Yeah. It is the line of the field. Now we have the tangent x dot equals b equals f df dz of fz 1. Yes, and then the energy E is no approximately if you raise the higher order terms, integral from 0 to 1, no, z from 0 to 1. Integral over n df dz dz x z where now here is also df dz times 1, but this is a vector going up, which is orthogonal to horizontal vector, so it vanishes. Dx, x is here, dz. Now, this integral differs only by notation. Instead of t is z. Yeah, so it is in the first approximation the same as the functional which we want to minimize in this earlier problem. So approximately this magnetic equilibrium in long cylinder, this problem is equivalent to the problem, two-point problem for the fluid, yeah, for the Lagrange equation. So we can apply our intuition. We will do it if you will survive in this course. Intuition which applies to both of these problems. And we'll see that no, after all, that in this problem, it is quite possible some sort of singularities. But this problem is relatively tame because for the generic Sakharov-Zaitsovich-Arnold problem, situation is much worse. Say the only conjecture which I saw about it in general is that in general solution is discontinuous on some dense set. You have a question? No, okay. Some dense set. No, okay. Now we can regard this as a long, I would say, introduction, and let us study this two-point problem. So what is, again, a classical fluid flow? So for any x in m and t time, we have ft of x, yes, in m, x in m, always 0, 1. So we can read it in two ways. If you fix x, then you have a trajectory of a particle, which initially was at the point x. If you fix t, we have some map from initial map of the diffeomorphism in classical sense of domain M. And so F0 is identity, F1 equals Fd. Now the straight way is the following, of course. Consider a sequence of let's call it balls. Yeah, like this. Such that the action of the case goes to infinite. Yeah. Minimize, minimize, minimize. That's the sequence. Okay. Approach. Maybe arrange. So, some minimum. No, our experience shows that we need some sort of compactness so that we can do it. But in the space D, space group of diffeomorphism, if you give some there some metric or some topology which is strong enough, for example, to ensure that all the maps are continuous, we cannot find such compactness. We have to consider much weaker, much more general, say, space where this D is compact. So I proceed to define this space of generalized objects, which is called generalized fluids. Which was introduced by Jan-Fred Brenier about, I think, 35 years ago. What is generalized flow? Generalized flow assume that fluid particles move more or less independent from one another. They don't form one flow. They don't even have some velocity field. They form something like a random process or random function. So we consider the following objects. omega. It is the space of fluid particles. The space in the simple case of diffeomorphisms is just the space M. We can say label the particles by their initial positions. Yes, at every point we have one and only one particle. But in more complicated cases, it is no more true. And omega in useful situations, it has its own structure, its own coordinates inside it, but they may have different nature. But what is important? Sigma algebra in omega. So some sets in omega are measurable. No, mean what is yes, one moment. And mu sigma additive measure in in or on sigma. So first of all, this measure is nothing but mass. So for some sets of particles, we can define the mass. For some other, we cannot. It is the space of fluid particles. No, this notion is wide enough to accommodate more or less anything which we need. It is a space of fluid particles. Now, for what is the flow? Generalized flow. It is no the following. I would say tuple G is a collection of omega, sigma, mu, and for almost all particles, so for almost all elements omega, we have its trajectory. Yeah, let us define omega t. Yes, so omega in omega f omega t for fixed omega, it goes from 0, 1 to the main end. Yeah. So what I defined here is nothing but the very general definition of random process. No, random walk in the domain M. And we will treat it as such, but we have to add some other requirement. So the first requirement is that it is incompressible. Incompressibility for O T. We have the map F T is, of course, sigma mu. Lambda is Lebesgue measure in M. Measurable. And F mu is lambda. So if you take the mu, how it is transformed by the map F at some fixed moment t, yes, then it's lambda. So its image is lambda. So this means that the particles are distributed at every moment in the domain M with the same constant density. No, we can always think that volume of M is 1 and the density is 1. Yeah. So it is the first, say, axiom. Second axiom, second requirement is the following, that the average action along the trajectories or the action of this general flow is finite. This means that, let me denote action of G equals integral from, integral over omega, integral from 0 to 1, f dot omega t square dt d mu. The mu is integration along omega is fine. And the third is the following: for almost all omega, we have the following x of omega 1 plus f of x omega 0. So it is the boundary condition. It is the finiteness of action. And the first is incompressibility. No, we can number them in other order. It doesn't change anything. So this is the minimal set of requirements which we need to work to approach this problem, two-point problem to minimize the action. Now, in particular example, for smooth flow of T, we have omega equals n. Yeah, here it is small space, but it's enough for a small. Omega equals n. Sigma equals lambda on m. So Lebesgue measure, no, okay, two-dimensional Lebesgue measure. In m, mu is lambda. Yes, what else? F omega t equals ft of x. Okay, omega. Omega is the same as x in this case. So for smooth flow, we have this thing.
How do you, how do you define position for this general? Okay, so
Excuse me?
what is x in point 3?
Where? In 3?
Yes.
Uh, ah, a moment. I think we have it said that I'm not changing. Our F of omega t trajectory F omega 1 equals, we have to introduce some other letter for the final configuration. Let me use F capital of F omega z. Yeah, thank you. So here it is all simple, but now we have to consider the general case. But I have to make one more some more comments. The second axiom, you see, it is something quite unusual in random processes, because usually we consider process like diffusion process and so on when this action is infinite. Yes, like the Brownian motion. So once upon a time, many years ago, I discussed this with Dinkin, who was a great specialist in random processes. And Dinkin refused to call these processes random processes. He said that it's so degenerate that it is not worth discussing this thing. So, in fact, it implies that almost all the trajectories are continuous in time. Yeah? Almost all are continuous. And so I want to introduce distribution. Of a generalized flow. What is the distribution? Consider the space X, C, 0, 1, with values in n. Yeah. Then almost every trajectory, or almost all omega, trajectory f of omega t belong to let me put belong to x, is element of x. Yeah. And so we have this map from omega to X, which is defined almost everywhere. Let me call this map I. Omega to X. Maybe later I'll find better notation. Omega to X. And this in X we have very sigma algebra. And again, in any reasonable case, our this map is measurable. And so we consider I star mu. Yes, measure in X. So we simply consider every trajectory as no as itself. It's called in the distribution of nice flow G in X. So what changed? The following changed. In the general definition, one and the same trajectory can be followed by different particles. For different omega, you can have the one and the same trajectory. Yes, and here all these omegas are divided in one, and this is what we observe. If you follow the motion of the particles, we don't see their internal parameter, internal coordinates, which are hidden, and the actual motion does not depend on them. We see only the visual motion of the particles. So it is a sort of co-meaning of generalized flow. And sometimes it is enough to consider the only distribution and forget about the more general, but sometimes it is necessary to consider the general framework with different interesting structures in the set of the particles. Yes. And a great advantage of this is that we can consider different generalized flows as measures. They are all defined as measures in the same space. So, and consider x equals c 0, 1, m. The D Borel sigma algebra. Mu, it is the measure in distribution and F. Okay, let it be F. It is funny that here the argument instead of omega, the argument is the trajectory itself. So it is a sort tautological map. You take what is the map trajectory corresponding to this trajectory. It is exactly this trajectory. Yeah. No, let us keep denoted by F for some time. It is, I would call distribution of G. Or we can consider it as generalized flow itself. Simply the space, instead of omega, we have the space X, and it is one for all the generalized flow which we consider. Okay. And now where we are about to prove weak convergence. Again, and how can we denote this? It is let us denote it by H. Yeah, it is also generalized flow. Yes, no. To mark that this flow has this fixed and standard particle particle space, I denoted by H. Yes. And now let us consider the minimizing sequence. H1, H2, and so on, such that H3 go to infinite. Yeah. And all HK conditions 1, 3. So we have a small, we have now a sequence of measures. So all H have the same particle space. It is the space of trajectories. Yes. The same sigma algebra there. They have different measures and have the same F, which is, as I say, tautological map. Yes, the silly tautological map. That the argument is a curve, a trajectory, and the result is that the same trajectory. What can be simpler? And the only thing which changes are the measure. So we can say mu1, mu2, so such that the action, now we can write the action of nu k goes to infinity. Action of UK goes to infinity. Now, we have the following thing.
Sorry, may I ask a question?
Yes.
So the action of nu k is just the square integral of nu k with respect to the identity?
No. We have the functional for the trajectory.
Yeah.
We have the functional its action, integral of square of its derivative, time derivative, yeah?
Yes.
So it is in fact square of its h1 norm.
Yes.
Yeah? And so the action is integral of this functional square of h norm, h1 norm, or against the measure nu k. We are closer and closer to some problem of linear programming. Yeah. Okay. So now what can be said about all these measures? We have the following thing. Action UK equals integral over omega, integral from 0 to 1, model. Now, elements of C are trajectories x of t. Which is denoted by x. Yes, so element of x capital are simply curves x of t. Yeah, so I will use this notation x dot of t square dt. So this is our functional, which is nothing but integral over omega norm x of omega h1 square dv. And let us recall that we started from some smooth diffeomorphism, yeah, and we have at least one smooth flow which reaches it with no, if we have no topological restrictions, with finite action. And now we take the flows which are whose actions are close, smaller than that. So this means that less than some constant. So we have bounded for all this sequence. We have bounded action, but the set. This is the mean value of mean value of this functional. This means that the set omega in x such that yes h1 is compactly embedded into x. Yeah. So the set of a omega such that S dot of omega H1 less than, say, y, mu is less than c over y. Yes, by the Chebyshev inequality. Yes.
Oh, but greater.
Excuse me?
Greater. No.
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 But it's bigger than y, yeah?
Bigger than y. Yes. This means that the sequence of measure UK is tight. No, it is this means that most of these measures is concentrated on a compact set. Yeah? It's the tight sequence of measure. Hence, UK is a weakly compact sequence. With the compact sequence, mu k j tends weakly to some, let us call it mu, as j mu goes to infinity. Let me like this. Right, bar, maybe I use new somewhere else. New bar. Yeah. So it is a weakly converges. And second, what we find is the following. The function so x goes to integral x dot t square x of t dt is lower than continuous. This means that x theta of t goes to x of t x means in c. Then x yes, so equal then in here x t. What is j equals j action. So no, this is more or less standard fact that this H1 norm is Laurent semi-continuous. And then this means from both this and this, we have that integral over x j of x, the mu bar less or equal than in no. Integral over x j d mu bar less or equal integral of x j of x d mu k. Yeah, but this sequence was minimizing, so this means that j of mu bar equals infimum j of mu mu prime condition 1 to 3. Incompressibility, finiteness of action, and boundary condition. Yeah, by the way, boundary conditions are also satisfied by this new because they are stable under weak convergence. Okay, so we find some generalized flow. First of all this scheme is ultra classical since our godfather Tonelli, and nothing new. And the result is some generalized flow. In this case, it is generalized flow in distribution of generalized flow. No, generalized flow coincided with its distribution. And the question is what it is. We got something, how it looks, and what to do with it. I tell you one example which I borrow from the work of Brière and describe how it might look. Example, M unit disk. X to minus x. Yeah, just antipodal map. And we are looking for the shortest flow connecting with these two positions, two fluid positions. No, you know what? Let me start from a simpler example. M is a segment in minus 1, 1. No, first of all, in the segment, we consider one-dimensional flow of incompressible fluid. It appears that it is impossible. The only possible flow is staying in place, because how else? But we don't have smooth flows, but we have a lot of generalized flows. So if you consider f of x equals minus x, so we are flipping this segment, then Brenier found a solution of this problem, which looked as follows. Let me draw it. Is x equals t, 0, 1. At initial moment, every particle in this solution explodes. It gives rise to a bundle of an uncountable number of the smaller particles, so to say. Each particle is moving in some direction, as if here we have quadratic potential. So, you know, if we start from here, it will move like this along sinusoid like this. If you take different shock and start from different point, then you'll have the same. It is the gold. And so for any point here. Yes. So here we have spontaneously the initial space of particle. It was just this segment, but then it spontaneously became two-dimensional, appears second parameter. Yes, and the particles, the different particles are moving like different streams through one another. We have continuum of fluid streams here. And so this is solution. Now he found analytical form of this solution. Now, in the case of 2D, M unit disk. Yeah. I need a lot of information. F of x equals minus x. Again, it is antipodal x minus x. Now, he found the following basic solutions. First, clockwise rotation. It's quite natural. We rotate it until it assumes the described configuration. Second counterclock. Rotation. And third, let me call it explosion. It is the following. The particle X explodes and gives rise again to a continuum of particles. Yes, these particles are moving in the parabolic field of potential. Yes, so they are moving along an arc of ellipse, and at the time one, they all together reach the opposite point. So it looks like this. No, and so on. So it is one point. If you take, say, other pair of points, this and this, then you have a similar picture. And so on. And imagine that for every particle we have this situation. At the same time, this particle explodes, it moves here, and this particle explodes, it moves back. Yeah. So we have three solutions, and they have all the same action. Yeah. So we can also take take any convex combination. We have here mu1, here mu2, and here mu3 are corresponding measures in the space X, in the space of trajectories. Yes, so we have these three measures, and we can take the convex combination. You take, say, alpha 1 mu1 plus alpha 2 mu2 plus alpha 3 mu3 mu equals alpha 1 plus alpha 2 plus alpha 3 equal 1. Yeah, convex combination, and it will have the same action and satisfy all conditions. So we have here a simplex in the space of measures, a simplex which provides us all solutions of this problem. I think it is brilliant. Yeah, it is so beautiful. And something like this happens in all other situations. In particular, if we consider the dimension, as you see, dimension doesn't play a role. The dimension of M can be arbitrary. And in 3 dimensions, I managed once to construct diffeomorphism F capital. Yes, of course, the same problem, such that solution, the minimizer does not exist among the smooth flows. The diffeomorphism was smooth, but the solution of this problem was true generalized flow having many streams which are crossing. That's it. And there is no smooth solution. So, so we have this interesting situation. But what I wanted to tell you right now, that this beautiful, infinitely beautiful picture, I think has little to do with any existing fluid flows which flow in the nature. So we have to consider something more, some more conditions, some restrictions which will give us something. No, a minimal requirement is that there exists velocity field. We can say what is velocity of particle at given point. And here, at any point, we have infinitely many particles with infinitely many velocities. Yeah, it is beautiful, but not from this problem. Yes, so what we found here is, I would say, parasitic solution, and we have to think what is the true solution, and this is what I will start doing next time, if you will survive by that time. Okay, have a good time.